All right, 5.4, solving special systems of linear equations. So remember that what we're doing so far in this chapter is we're finding the point where two lines cross, right? We're finding that point. We started off by graphing, and then we used substitution, and now we're using, and then we used elimination after that. Now we want to look at some special case scenarios. Everything that we've looked at so far has been one solution. The lines intersect, and then you could also think about it as they have different slopes, right? The lines intersect one time, and the one time where they intersect, that's the point, and that is our answer, right? Every problem we've done so far has fallen into that category. But we also have two other categories that they could fall into. We could have no solution. What if the lines are parallel? What if the lines are parallel? Well, they would never cross, so they'd have no solution, right? That should kind of make sense to us, right? So we had one solution where they cross, no solution where they don't cross ever. And then let's look at the next one. We have infinitely many solutions, and that would be if they happened to list the same line twice, right? And they don't necessarily have to look exactly the same. It could be something like they have like y equals x, and then 2y equals 2x, right? I could turn either of those into the other one by either multiplying or dividing by 2. So it's not necessarily, they're not necessarily going to give you the same exact line every single time, but they'll give you two equations that you could manipulate to turn into the other one. So that would be infinitely many. So these are our three scenarios. We could have two lines that cross at a point. We could have two lines that are parallel and never cross. Or we could have two lines that are actually the same line. So they lie on top of each other and they have infinitely many solutions. Normally, I like to write this infinitely many as infinite solution. And that's a little bit faster to write for me. So, example 13. Let's look at it. This should be y equals 3x minus 2 and y equals 3x plus 2. So we're supposed to solve this. And let's look first. They have the same slope. They have the same slope, which means that they're parallel, right? So this should be no solution. Let's make sure that they're actually different lines. This is a -2 and a +3. So you don't have to sketch this, but what this would look like would be a line like that and a line something like that, where they would actually be parallel lines, and this one would have no solution. All right, example 14. This should be 3x plus y equals -4, and 9x plus 3y equals -12. Looking at these, I notice that 3 to 9 is multiplying by 3. 1 to 3 is multiplying by 3. -4 to -12 is multiplying by 3. So if I were to take this top one and multiply by 3, I would get 9x plus 3y equals -12. And this is exactly the same thing as what's down there. So these are actually the exact same line. So if I were to graph them, they would lay on top of each other. So this is infinite many solution. Right? Because every single point on those lines would actually be a solution. Let's look at the next one, example 15. This one should be -x minus 4y equals 10, and x plus 4y equals -10. Now, well, we could eliminate these, right? We could add these together and eliminate them. I have a -x and a +x. That would be a 0. That one eliminates. -4y and +4y would be 0. 10 minus 10 is 0. So we got 0 equals 0, which kind of looks like infinitely many solutions whenever we've done that before, anytime we get a true statement like this. Let's look back up at them and see if they're actually the same line. If I were to take this top piece and multiply by -1, I get x plus 4y equals -10, which is exactly the same thing as what this other one's listed, right? They're opposites of each other, or they multiply by -1. So this one, again, is infinite solution because they're the exact same line. Example 16. This one is -x plus 2y equals 3, and 2x plus y equals -6. Let's solve this by substitution. I'll get that y by itself, so I'll have y equals -2x minus 6. And then I'm going to take this and plug it into the other y, so I'd have -x plus 2 times -2x minus 6 equals 3. Distributing the 2, I'd have -x minus 4x minus 12 equals 3. So -5x equals 15, and x equals -3. So right now we should be able to say that this is not a special case scenario. These two lines cross, and they cross at a point. Okay, I'm not finished with the problem yet, but make sure that just because we have these other two, the blue and the pink special case scenarios, we can still have regular plain old lines that cross, right? Just because we've learned these two new things doesn't mean we don't have points anymore as our answer sometimes. So let's finish this one. We'll plug back in. I'm going to plug into this guy here. So I'd have, what would that be? Y equals -2 times -3 minus 6. That would be 6 minus 6, which is 0. So my point is -3, 0. And we are done. So here, this one had one solution. This one had infinite. This one had infinite. And this one had no solution. Make sure that you don't forget about the one solution, right? Sometimes whenever we learn some new things with the infinite solutions and the no solutions, we forget that we can have plain old simple lines that just cross, right? Don't forget about that. All right, that's all.